Hello, I'm Royce Pfeiffer, and the reason I'm making this video is because I find it irresponsible for me to not make this video. And the reason for that is because I've looked into a lot of physics stuff and I understand all of the working basics of the physical universe. And I think of it as being completely irresponsible for me to not put it on video so that people can see and understand it, just in case something happens to me, like I die in a car accident or something like that. Because we're all limited human beings and we really don't know the time of our death. Now, it sounds stupid for someone to say, oh, I know all of the basics of the physical universe. How could that possibly be the case? And it does sound ridiculous, but I definitely do, because it's a lot more simple than what physicists are making it out to be. Now, well over, I think it's been about 200 years, well over maybe about 200 years, there was a theory that everything came, let's see, all physical happenings happen, no, I'm not sure about how much they actually understood. But I do know I understand a lot more than what they understood. They figured that light passed through a medium. There was a medium through which light travels. And indeed, this is definitely the case. Light only travels through a medium. See, at the time of Einstein, they were saying, well, light, they noticed that when light traveled, it travels like a wave. But when light impacts, it impacts like a particle. And during that time, the time of Einstein, they said, okay, light travels like a wave and it impacts like a particle. So they said, it's just, they called it the duality of light. And they didn't know why that was, and they said, well, we're smart. If we can't figure it out, nobody can figure it out. It's just weird. It just does it somehow. Somehow light is both a wave and a particle. And later, photon theory, photon theory emerged from that. I don't know when it emerged from that, but photon theory emerged from that, where photons travel like a wave and impact like a particle. The simple thing about it is that light travels like a wave and impacts like a particle because light is a wave in particles. It's really that simple. But there's a lot more than that I know about this ocean that we're all in. We're actually in an ocean of dust. I often refer to it as an ocean of matter, but it really is just dust. And all of the physical happenings spring from this ocean of dust that we're all in. It's responsible for gravity, it's responsible for electric attraction, it's responsible for electric repulsion, it's responsible for radiation, it's responsible for every physical force, every property of matter that this ocean that we're all in. And we're just fish in this ocean. In fact, even inertia of rest and inertia of motion prove this. So, like, here's an easy demonstration. You can actually feel this ocean of matter that you're in. If you take your hand and you go like this, you can actually feel the blood shooting out down the length of your hand, and the blood comes and it whips right down to the edges of your fingertips, and you can feel it. And that's because you're like a screen door to this ocean. You can touch, you can tag this ocean, and you can feel the ocean that you're in. And it's not just the air. it's the stuff that's smaller than the air. It's the stuff that, it's the particles that are between the air. It's the stuff that exists out in outer space that people thought was empty but is not empty. This ocean of dust that we're all in, there's nothing special about it. It's just dust. It's like what the Bible said when God is referring to the body of Adam. He says to Adam, about Adam's body, dust you are, and dust you will return. Referring to Adam's body, not referring to Adam's spirit. The spirit lives forever. The spirit is the real you. So, this ocean that we're all in, like I said before, it's responsible for everything. It's responsible for gravity. It's responsible for inertia. You can feel it. You pass through it, and it passes through you, but it also clings to you, and that's why inertia of rest and inertia of motion happen, because when you're start to go, it's hard to get going, and the reason for that is because you're pushing on the ocean of matter. But once you try to stop, it's hard to stop because you've established a flow in the ocean of matter, ocean of dust. And so what happens is that the ocean of dust pushes on you. And there's nothing special about this dust. It's just dust. The only special thing about this dust is that it is, it's the closest thing that I can say about the dust that people could probably understand is that it's space, time, and matter in a fully existing form. To be perfectly accurate, it is a piece of every piece of dust is a piece of existence. And the reason it has to be a piece of the reason it has to be a piece of existence is because like space-time matter, is because there has to be space to it, or else it's not found anywhere. And it has to have time to it, the present time, or else it's found at no time. And it has to be a substance, it has to be real, or else it again doesn't exist. So there's three things that this dust is. It's space, time, and substance, or you could say space-time matter. It has to be real. So in other words, I'm saying that the dust is real when I say that it's a piece of existence. But here's an interesting thing about something that's real, that consists of both space, time, and substance. And that is that not only when it's just sitting there, it's showing you what it is, but it also shows you what it is if you displace it in a line. Now things get interesting here when you displace matter in a line. Like, for example, say here's a piece of matter, aka a piece of dust, aka a piece of existence, and say here's another piece of existence that pushes it like this, in a line. Now if you push this piece of existence in a line, you will get linear time out because you pushed it in a line. So you get linear time out. But you also get linear space measurement as well, because you pushed it in a line. So you get a linear space measurement out. But you also get substance. Let's see, how does that work? Well, it's there, existing among matter, but it always exists among matter. Yeah. But it's interesting that you get linear space, linear time measurements out of it by displacing it in a line. In fact, that's the basis of measuring linear time, like with clocks. All clocks work like this. They all move matter, aka dust. That is a piece of existence. And that's why they are able to measure time, is because they're measuring the time inside the clock. In a pendulum swinging clock, it would be the pendulum that keeps the time. In an electric, let's see, a piezo. No, yeah, they do use the piezoelectric crystals. Of course, they also use it. They also time it with the vibrations of the wall. Most electric clocks use the 60 hertz from the power company to keep time, but there are standalone clocks like electric clocks, like little watches that you wear on your hand, and they measure time using a crystal. They use the vibration of the crystal. The crystal, goes back, forth, back, forth, back, forth, and that's how they measure the time. Yeah, when the crystal bends one way, it will eject electrons off the pinched side, and then the electrons whip around and go here, and then it goes back the other way, and then electrons travel back. So it's going bloop, 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 bloop as the crystal goes bloop, 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 and that's how the timing in like a little wristwatch works. So it's always about moving matter. That's how all clocks keep time. And you can see why is because they're displacing time in a line. They're like, because any piece of existence, any piece of dust, in other words, that actually exists, any piece of existence that is dust, if you displace it in a line, then that piece will give you a linear time measurement out and a linear distance measurement out, which is, linear space measurement out, which is distance, yes. So that's how space and time work. And the funny thing is that from the perspective of, and this is a little deep, but you might not get this, from the perspective of the dust, from this perspective of the object, it doesn't move relative to itself. So it always just exists. The piece of dust, it's always just there. It never moves relative to itself. Of course, nothing does. And that part's not the hard part to understand. What's interesting is that it is a piece of the forever present. It's a piece of forever. It's just, it's always there. It always exists. Because we did inertia of rest and motion. Yeah, time to move on to gravity, I think. So with gravity, it's actually very, very simple. Gravity is not a field. It can be seen as a field, but it's not a field. It is an arrangement of matter in the ocean of matter. Every single thing that's a field, that appears to be a field, is actually an arrangement of matter in the ocean of matter. And so the scientists out there, the physicists out there, they don't believe in the ocean of matter. It's like not believing in God. If you don't believe in the ocean of matter, you can't explain basically anything. You would think that gravity is a fundamental force of nature. It's not. You'd think radiation must be a fundamental force of nature. It's not. You'd think inertia of rest and inertia of motion are just laws. They're not. They're all caused by something. And they're all caused by this ocean of matter that we're all in. So, let's see, gravity. Oh, right. If I had some balls, I could show you better how it works. Because all the pieces of matter in this ocean of matter are balls, are spheres. And the reason that they're spheres is because that has the least amount of surface area on it. Yeah, the least amount of surface area on it. That's exactly what I wanted to say. And that's very, very important. Why? Because the internal pressure of the sphere, the sphere, always wants to blow out. And to keep it together, you have to apply pressure. to the sphere on all sides. But the only way that you can apply pressure to sphere on all sides is by other little balls. And that's exactly what happens in the ocean of matter. But this also explains radiation. Yeah, I should explain radiation before I explain gravity. Okay. With radiation, say you have an object that's just a little too big for what's pushing in around it to hold it together. Then what happens is the internal pressure finds a hole in the ocean of matter and it pops off a piece. And then it finds another hole and it pops off another piece. And that's why radiation is a little bit like, it's calculatable, it's measurable, it's predictable, but it also can be unpredictable as well. And that's, by the way, why things, they think things pop in and out of existence on a very, very small level, smaller than quarks, smaller than electrons. They think that objects, that matter may pop in and out of existence, but that's just because they don't see the smaller pieces. There's always smaller pieces there, but when those pieces collide and become larger pieces, then they can see them, and they're like, oh, there's a piece that spontaneously made itself. But then when that same piece flies apart, they're like, oh, now that piece flew apart. But they don't say it flew apart. They say, oh, they see the reaction of it bumping other things around away from it, and they say, oh, look, energy, it turned into energy. But there's no such thing as energy of that type. Matter cannot become energy, and energy cannot become matter. That kind of energy doesn't exist. Things don't pop in and out of existence. They always exist. They're just pieces that are too small so that they don't understand that those pieces do actually exist. Now, when you look at the smallest pieces that go in and out of what they think is existence, there is a general rule of the general pressure of the entire matter universe that pushes in. It's responsible for all the smallest average pieces. So you get all the smallest average pieces, and this results in the general pressure of the entire matter universe in any particular area dictates the average size of the smallest pieces. Now, those average size of the smallest pieces dictate the next step size up smallest piece. And those next step size up smallest pieces dictate up the next smallest size pieces of matter that exist. And so on and so on and so forth until you get to the size pieces that are so big that we actually detect them. Those also are electrons, and then the much larger quarks that make up the proton, and so on and so forth. You know, even atoms, and we can actually see the atoms are made up of protons and electrons, and it looks like to us that electrons are very, very far away from the nucleus, but they're actually, here's an electron and there's a bunch of stuff around the electron that's small, and here's the proton and there's a bunch of stuff around the proton, and the stuff around the proton is small. But what's around the proton is the pieces around the proton are much larger than the pieces that are around the electron, which are even smaller. And so you have this cloud of dense stuff because the pieces are larger around the electron, holding the electron together. And around the proton you have even larger pieces that help hold the proton together. And the reason for that is because of the fact that a large round ball like this has a flatter surface than a smaller ball, and this is also the premise of gravity, but it's also the premise of electric attraction, because the ocean of matter pushes things into holes. You see, every single interaction in the entire matter universe has to do with particles being pushed into holes, and that's it. There's no magic to any of it. If there's a hole, the matter will get pushed into it. And this is extremely simple. There's no other interaction in the entire physical universe. So what happens is the cloud of stuff that's around the electron, the tiny pieces that cling to the electron and around the electron, cling there due to a gravity, but it's not a gravity. It's actually a large piece-fitting game, because the larger, flatter surface of the electron is covered better by larger balls. Now, the largest ball that would cover the electron, it would be something like this. Like say this is the surface of the electron, and so you'd want something to cover it that would go like this, and that would fit the best. But you don't have a concave to fit the convex of the electron. All you have are these teeny tiny balls available. So these teeny tiny balls cling, which are much larger than the rest of the ocean of matter, that are clung around the electron. And they don't go just on the surface of the electron, oh no, because these balls also have their own atmospheres around them. Just like little bitty atoms. And so these little bitty clumped up atoms are all around the electron, but they're still much smaller than what's around the proton. Now the proton, it has larger balls than the balls that are around the electron. And so what happens is, and this is a very interesting interaction, is that the pieces that are around the electron fit well with the pieces that are around the proton. And so what happens is, this cloud is attracted, but actually just pushed together by the general pressure of the entire matter universe pushing in on them, pushed to fill each other's holes. This electron's cloud is pulled in to the proton, and so the proton's cloud, and so the clouds like each other, they want each other, and so when the electron goes towards the proton, it goes towards the proton and stops right around the proton. And that's why when you release an electron, when you have an electron here and a proton here, and this proton has no other electrons, when you release the electron here, the electron is supposed to attract directly to the proton, is what the current theory is, but that's not what happens. What happens is that the electron goes towards the proton, and it goes boing, 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 and the clouds, the two clouds envelop each other, and then it's stable, and then you've got this one hydrogen atom, and so the two clouds neutralize each other, and what it's really doing is it's filling each other's holes. Again, it's all just a dust. It's all just a piece-fitting game. There's nothing special about the proton other than its size. There's nothing special about the electron other than its size. If you chopped up a proton smaller than the quarks that make it up, smaller than the other pieces that make it up, if you chop those pieces up to the size of an electron, they will be an electron, because electrons do not have charge, protons do not have charge. They have clouds. They have, in this ocean of matter, aka they have larger pieces that fit their larger pieces. That's how electric attraction works. Now, how gravity works is the same way, except that instead of having a particular size, a particular class of particular size dictated by the general pressure of the entire matter universe going all the way up to the proton, what we have with gravity is the same basic sizes. You've got atoms down there on the Earth, and so gravity, it distorts the ocean of matter by having a large surface, again from the atoms. So what happens is that what it's doing in the ocean of matter is that if you have a large surface, that the only good thing that that covers that surface is other large other large pieces, which is why large pieces come together. And the reason large pieces come together is because of the distortion in the ocean of matter, or aka ocean of dust that we're all in. In other words, in the pieces of existence that are here. Again, it's all just a marble fitting game. It's all just pieces of stuff. So say you have this ball here on Earth, and or you know, you have many balls on Earth, large ones. And again, the best thing that covers them is to cover this convex surface is a concave surface, but you don't have a concave surface. So the next best thing would be a flat surface, but you don't have a flat surface. So the next best thing is a large piece of matter to cover the holes, and then there's some tiny stuff would go between them as well. So you got this large piece fitting best with this large piece. Now once it goes like this, then it doesn't go any further. But it does want to reach down, and the reason why it wants to reach down is because the large pieces around the large pieces fit well with the large pieces that are down here lower. And that's why many things will clump together. Now, let's see. This ends up being like large chains reaching way up into outer space. And the reason for this is because these large pieces have large pieces around them. Those large pieces have large pieces around them, and so on and so forth and so forth and so forth, all the way on way up into space. And so it distorts the pattern in the ocean of matter that we're all in. And that's the simplicity of gravity. And the reason for this is, I wish I had 3 balls I could show you, but it's because of the larger holes that are around larger pieces of matter. See, when they talk about black holes, they call it a hole, and that's not completely untrue. But it's like saying the glass is half empty when you could say the glass is half full, because if you have anytime you have large pieces of matter, you're going to have large holes. Like here on Earth, when we have large pieces of matter, we have large holes between the large pieces of matter. I wish I had 3 balls. Okay, you're just going to have to imagine 3 balls. Here's a ball, here's a ball, here's a ball, and actually a 4th ball behind it, and there's a ball. And between those 3 balls, 1, 2, 3, and 4, there'll be a large hole here. Now, if these were smaller balls, 1, 2, 3, and 4, there would be a smaller hole between those 4 balls than there would be a larger hole between larger balls. And that's why you have gravity having a much larger, much stronger, much wider reaching effect into space every time you have larger balls clumped together, because it literally distorts space. It's just like what Einstein said, and Einstein wasn't wrong about this, is that space and time cause gravity. And he's right. Space and distortions of space-time. Gravity is a distortion of space-time. He just didn't realize it was literally a distortion in matter, and that's kind of the breakthrough. See, Einstein, he understood that space and time were one thing, but what he didn't understand was space-time, matter are one thing. They're not 3 different things. No. The space, time, and matter are one thing, not 3. And again, like what I talked about towards the beginning, is that you can't have space and time and matter being 3 things and... Actually, I didn't cover that. Okay, you can't have space and time and matter being 3 things and have it exist. Wait, I kind of did cover that, sort of. Yeah. Because, yeah, I do remember now, I did cover that, because if you have space all by itself, then it's not a real substance, and it's not a real... Yeah, if you have a piece of space by itself, which you can't do, because it doesn't exist. And the reason it doesn't exist is because it doesn't exist as an actual thing, aka it's not a substance, it's not matter. If you have a piece of space without time, again, you're not going to find it anywhere, because it doesn't exist in time. and it's, in other words, it's not a piece of the present. And if you have time all by itself, it's not going to be found at any place because it has no place to it. And it's not going to exist as a real substance because it has no real substance to it. And if you have substance all by itself, you're not going to have space. You're not going to, yeah, it's not going to be found anywhere, at any place, at any time. And so again, it doesn't exist. So you have to have all three for any piece to exist. I pretty much covered that before, but I think I added more details that time. Okay, let's see, back to gravity. So the gravity is, yeah, like great chains coming up from the Earth, reaching way out into space. Same thing with the sun. And that's the reason why all of the planets spin counterclockwise as viewed from the North Pole, because the great chains that come off of the sun, which is just a dense amount of matter, of stuff, of dust that's around the sun, is also around, there's a bunch of stuff that's around the Earth. So when the Earth orbits the sun counterclockwise as viewed from the North Pole, this causes a counterclockwise spin. Why? Because the ocean of matter that's densely around the sun, due to it being a very large, very massive object, it is interacting with the Earth, and the stuff that's connected to the Earth also interacts with the sun, and so it goes around in a counterclockwise way all the way around the sun. So if you have a counterclockwise spin orbit, that results in a counterclockwise spin. But it also, interestingly enough, causes friction, because anytime gears are going like this and interact with each other, they heat up. So with it going around the sun, we actually heat up the sun a little bit, and the sun heats up the core of the Earth. See, people used to think that the core of the Earth, when the Earth slammed together, that caused the core of the Earth to be hot. But no. If that happened, it would have ended thousands and thousands of years ago. That heat in the core would have dissipated into the Earth. No, it's constantly being refreshed. The core of the Earth is hot only because of its orbit around the sun, causing its counterclockwise spin as it's crashing into all this ocean of matter that's around the sun, because it's attracted to the sun and yet has the inertia so that it never goes into the sun. But it's very stable because, and this is another thing they don't get, it's very stable because of the ocean of matter that it's in as well. Because of the in-out thing. Because otherwise, if it wasn't that way, what would happen is the sweet spot would be an exact point. Like, if inertia was if inertia was just a law and not a reality, and of course that's impossible. Everything has to have a reason for being. But if inertia really was just a law, then and gravity was just a law, and of course that's not true, as I've already explained. Then what would happen is, if you had the sun here and Earth here, if the Earth was just a teeny tiny bit too close, it would spiral into the sun and crash and burn up in the sun. If it was just a teeny tiny bit too far away, it would spiral out into space and we'd be lost in space. But because the ocean of matter gives us leeway, because it's actual real stuff as a buffer, with matter filling holes, that it's firmly established, just like the Bible says about it being firmly established. But that means that the sweet spot is wide instead of a single point, and that's due to the ocean of matter that we're all in. What else? Let's see. Gravity, covered gravity. Radiation. So yeah, step sizes. I covered radiation a little bit. The reason why things radiate away is because you've got step sizes. and the step sizes, the reason you have step sizes, remember how the smallest stuff is dictated by the general pressure of the entire matter universe pushing in on it. But and that determines the next step size up that can hold together safely, because those pieces gather around it and help hold it together. So it can get its clumps together to a degree that, and make a ball large enough to a degree that it will hold together. And then if you get it too large, what happens is the pieces that are around it whip around the piece and take it away, and that's radiation. But that's also, okay, yeah, because there's many different forms of radiation. That's also the kind of radiation that is seen in like beta radiation or alpha radiation, that kind of thing, because it all has to do with this different size pieces, and so when the object gets too large for the environment that's around it, that's holding it together, it doesn't hold together. The pieces that are there around it fill in, and filling in their own little holes, rush in between the large piece and the small piece and take that piece away. And that's why the ocean of matter is responsible for radiation, because the smaller pieces rush around the little piece, and in so doing literally push this piece away. That's radiation. Now in fusion, the opposite of that happens. In fusion, if you have too small of an object and another too small of an object, if they get too close, poof, they stick. They stick together because they're covering each other's surfaces. So they're actually filling a hole, and the stuff that gathers around it, is pushing in on it, and it becomes a large atmosphere around the object. And that's what we see happening in the sun, and that's why the sun is bright. But why is the sun bright? Well, because when those two pieces, those two hydrogen and those two protons stick together like this, poof, like that, it ejects the fine stuff, and the fine stuff gets ejected all the way around, and it gets splurted out into space. And what that does is it hits this stuff, which 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 drops off at a square, yeah, it goes like this, like that. And so it gets weaker and weaker as it goes out into space until it hits Earth, of course. But it's actually the wave is actually, you know, kept, but because the area gets larger, any little point is of the brightness gets weaker. Anyway, and that's why the sun is bright, because of fusion, and that's how fusion works. But you can see it's really just dust. There's nothing special about this dust. It's just dust, and it's responsible, like I explained, for gravity, for electric attraction. I don't think I covered electric repulsion. I just covered radiation, though. Yeah, I just covered fission, which is radiating out, and fusion, which is fusing in. Did I cover... I don't think I covered electric repulsion. Electric repulsion. With electric repulsion, okay, say you have two protons, and this ocean of matter, this ocean of stuff, is around this proton, and here's another proton, and there's an ocean of stuff around it, a dense cloud of stuff. The issue, the problem is that these balls are basically all the same size. Now it's actually a little more complicated than that, because like I described before, if you have a proton like this, then you have balls around it that are about this big. That it's actually much smaller, but just so that you can see it, it's like this, and then around those balls, teeny tiny balls like that, and then around those balls, teeny tiny balls like that, and then around those balls, teeny tiny balls like that. So there's many step sizes until you get to the smallest step size, which is dictated by the general pressure of the entire matter universe. Anyway, So you say you have a proton here, and you have a big clunker here, and a little clunkers there. That on and on and on. But the proton collects the larger pieces from this ocean of matter, and they're all basically the same size. Even in the step sizes, they're all basically the same size as they go down and down. Now around the electron, the same exact thing happens. Only their step sizes are even smaller step sizes, which is why the it fits around into the holes of the cloud that's over here, and thus neutralizing that cloud. But if you have two protons, like a proton here and not an electron, another proton here, what happens is that this cloud doesn't fit into this cloud because they're all the same size. The pieces in the cloud are all the same size. It already has what's fixed in that cloud and can't get any more. So if you push two protons together, the ocean of matter pushes up, pushes down, pushes in, pushes out like this, and then they will spring away. And the reason they will spring away is because the ocean of matter is not filling holes. You're pushing the finer stuff. You're pushing you're pushing the finer stuff out like this, and that's why they'll spring away. That's electric repulsion. Yeah. And what else? Let's see. Inertia of rest, inertia of motion, gravity, electric traction, electric repulsion, fusion, fission. Oh wow, magnetism. We didn't cover magnetism. Magnetism's really interesting. Magnetism was the hardest thing that I'd ever put my mind to understanding. I think of it as the Mount Everest climb there, because it was the hardest thing for me to understand, to figure out. It took me months to figure that one out. That was a long one. Well, I don't know if I can do this without drawings, but yeah, of course I'll give it a shot. Magnetism. Okay, when an electron is traveling through the ocean of matter, what happens is it's like a motorboat, but instead of being on the surface of the water, it's underneath. We're all in an ocean of stuff, an ocean of matter. So what happens is with the electron, when you're going like this, the electron's traveling through this ocean, it leaves a low pressure behind it. Why? Because the electron moved away from the ocean. So it's leaving a low pressure a wave that streams off the tail of the electron. At the front of the electron, it's slamming into the ocean of matter. And so on the front of the electron, it's a high pressure coming off of the front of the electron. So what happens is you've got this electron traveling like this, and I can see my battery's low on my camera, but I'll try to speed up. Okay, so the electron is going through the ocean of matter. It's going like this. You've got the low pressure streaming off the back, the high pressure streaming off the front. And what happens is, and this is very important, is the shape of the wave. It's not only a cone shape coming off of the electron, but also the high pressure part is smushed in the direction of travel. So the high pressure part is strong in strength, but short in length. It's the opposite of the low pressure part that's streaming off the electron, because the wake that's being left by the low pressure part that's streaming off the electron in a cone shape is that the electron is, the low pressure part is long in length but weak in strength. And this is critical because when this wave comes off of the electron that's traveling through the ocean of matter, and it's just stuff, is that you've got the long low pressure streaming off here and the high pressure on the front. And so what happens is when that part hits when the electron when that wave hits another electron that is loose, the high pressure part bumps the electron away just a bit, but then what happens is it will accelerate towards the low pressure part. And why? Because a loose electron, it's got all its stuff around it, and it's massive, and it's able to be better accelerated by the low pressure part of the wave, because it's being sucked into it. It's really being pushed in by the general pressure of the entire matter universe pushing in on it, but you could say that it's being sucked in to the low pressure part of the wave. And the reason it gets sucked more because it's longer. It has a longer time to accelerate into the lower pressure. Why? Because it's loose. So the loose part accelerates into the low pressure part of the wave. Now, if an electron is stuck, though, if the situation is the electron is stuck in a hole instead of loose, the opposite of loose being stuck, then the thing that affects the electron the most is that when the smushed up high pressure hits the stuck electron instead of the loose electron, what happens is it's like a hammer, and it pounds the electron right out of its hole. And when that happens, the low pressure, the high pressure part of the wave pounds on the electron and sends it flying, and it sends it flying away, and it doesn't get affected by the low pressure as much. Why? Because it's already popped. It already has an acceleration to it, and it pops it right out of the hole. Now when it's stuck, though, the low pressure part of the wave, it can pull on it, but it won't pull it out because it's stuck. So when the wave keeps repeating, if you have like a repeating wave, then it's gonna not be accelerated by the low pressure part of the wave as much as, backwards, as much as it's gonna be unstuck by the high pressure part of the wave. So if a stuck electron experiences the low pressure part of the wave, it'll go try to get out of its hole. It's not going to get out of its hole. It's not going to do anything. That low pressure is going to travel on. The electron is traveling through a wire, perhaps. Let's say it's going through a wire. It's making a wave that comes off of it, streaming off of it in a wake, but it's a three-dimensional wake because it's in a cone, because it's below the ocean, like in a submarine. And when you have a loose electron, it's better accelerated by the low pressure part of the wave, and not very accelerated by the high pressure part of the wave, because it's got all the stuff around it, and therefore it's acting like it's more massive. But one that's stuck in a hole is better accelerated by the high pressure part of the wave, and the reason for that is because the high pressure part of the wave is like a hammer. When it hits it, it's short in length but strong in strength, and it's strong enough to whap that electron right out of its hole. Now this is very important because there are two kinds of affected electrons that do better in this scenario. Like, for example, when the incoming wave from this moving electron that's moving through this wire, when this incoming wave hits a loose electron in, say, another wire over here, perhaps it's a copper wire or an aluminum wire, some conductor that's really good. Is my battery about to die? Yeah, it is. Well, anyway. When it hits this loose electron here, when the wave does, it will accelerate this loose electron towards the incoming wave. Why? Because when the high pressure part bumps it back just a little bit, it passes it, and then it gets sucked into the long, drawn out low pressure part of the wave. And that's important because the high pressure part is short in length but strong in strength, and it's equal to the low pressure part of the wave, which is long in length but not as strong. low in strength. But for more massive objects like loose electrons, they have all their stuff around them and not stuck in a hole. They are better accelerated by the low pressure part, and that's why when this electron is traveling this way in this wire, this electron will travel this way in this wire, and that's important to know because that causes the high pressure, this low pressure part was satisfied by moving this conductive electron, but the high pressure part of the wave was not satisfied simply by bumping the electron back a little. Oh, no, no, no. Why? Because it travels onward, the high pressure part. And what it does is it travels on until it hits a stuck electron inside of the atom. See, let's look at a copper atom. The copper atom, it's got one loose electron on the outside. The rest are pretty well stuck close to the center. And that's another thing, is that people think of electrons as all orbiting the nucleus, and they're not. Only the outer ones do when they're pushed. The outer ones, an outer electron can orbit the nucleus, but they don't orbit all the time. They only orbit when they're pushed. But that's also what allows copper to be malleable. Malleable is because it can change its connections to the adjacent atoms by moving those connections around. So it's both malleable and conductive that way. Why? Because it only has one loose electron, the outer, for bonding between atoms. But that loose electron is then able to jump between atoms as well. And so when it's jumping between atoms and it feels the incoming wave, and then it is sucked in by the low pressure part of the wave into the long drawn out hole, and so its stuff, it's satisfied. But the other electrons deeper inside the atom are not. What's going to happen is the loose electrons that are in a piece of aluminum, they are going to accelerate towards the incoming wave, and the reason for that is because they're loose. The electrons in the aluminum or any really good conductor are loose, and what's going to happen is they're going to travel towards the incoming wave from the electron, because when the high pressure part of the wave hits them, they get bumped back a little, but as soon as they sense the low pressure part of the wave, which is long and drawn out, it's better able to accelerate them because it's a longer drawn out wave. And so that electron is accelerated towards the incoming wave. But what is not satisfied by the aluminum is the high pressure part of the wave, and so it travels on and it hits an electron that's closer to the nucleus than the electrons in the outer shell, and it hits one of those the high pressure part hits one of those electrons, and it's absorbed by bumping the entire atom back. And so what we see is if you have a lot of incoming waves from a lot of incoming electrons traveling down this wire, this piece of aluminum will be bumped back away from the wake of this electron that's traveling by, or a bunch of electrons with a bunch of wakes traveling by. So that is why a piece of aluminum or any conductor, like copper, silver, gold, will be thrown back away from an electromagnet. Now the opposite happens with iron. See, those other conductors are diamagnetic, but they're actually inconsistently diamagnetic, because unless it's like a really, really good conductor. And the reason for that is because at high temperatures, even in copper, there's if the waves are weak, the electrons travel around and they hit resistance, because they keep running into stuff and jamming up inside the conductor. But if you have a really good conductor, like a perfect conductor, then it will be consistently diamagnetic. Now you also have you don't need a perfect conductor to be consistently diamagnetic. For example, bismuth is a great example of something that's not a good conductor, but is powerfully diamagnetic. And the reason is because inside the bismuth, there's a crystal structure inside between the atoms, which allows for an encasement of an electron, one of the outer electrons inside a case, where it's shielded from all of the junk that's happening inside. So these electrons are not bumping between atoms like it does in other conductors. It's around inside a single atom. When the incoming wave hits it, it's large enough and loose enough that it whips towards the incoming wave. But then when it hits the incoming wave, the rest of the hard wave, it travels on until it hits the high pressure part of the wave. It travels on until it hits a stuck electron, and then it bumps the bismuth back. And so because of this encapsulation inside its own atom with bismuth, it can be consistently diamagnetic instead of just non-consistently diamagnetic. They don't even talk about this. There's no words for it yet, but that's indeed what happens, and that's why it happens. Now with iron, like I was about to say, with iron it's the opposite effect. It also is encapsulated between the electron that's affected is encapsulated inside the atom. Now they'll teach you crazy stuff like because they don't know what's going on in the electronics books and such. And I read what they said in college, and when I didn't know better, I just I read it and believe it, But after college, I really wanted to know how the rest of it worked, and I looked into that, and that's how I found out all these various things, because I really wanted to know for my sake. I wanted to know because I was a true scientist. Well, anyway, so when you look at iron, you're looking at like the affected electron that's in iron is like the affected electron in bismuth, except that in the crystal of iron, the way it's arranged in kind of like it's like an octahedral shaped bonding, where on the outside of the atom it is. So because this is also, they recognized, is that for something to be magnetic, attracted to a magnet, it had to have two outer electrons, and there's a very simple reason for this that they don't know yet, and I'm about to tell you why. The one outer electron is the binding between atoms. The other electron is beneath that electron, inside a shell, an encasement made by the other single electrons bonding all the way around the atoms. This is why if you take iron and connect it to sulfur atoms, it's no longer magnetic. Now, according to the current theories, it should be magnetic because it has they think it has to do with the domains, and it's all just has to do with magnetic domains, and but the issue is, and they'll think, oh well, maybe it messes up the domains or something. It has nothing to do with domains, nothing to do with their version of what it does. They did recognize it did have to have two electrons in order for it to be magnetic. That is correct, and good for them for realizing that. But the reason for that is because the one electron is the binding between atoms in an octahedral shaped crystal, forming a kind of a cage around this other one that's inside the cage. Now the other one inside the cage gets stuck in a hole, unlike the bismuth, the ones in the cage of the bismuth atom. The ones in the cage of the bismuth atom are loose. The one electron is loose inside the cage. This one, no, it's stuck in a hole inside the cage. So so it's not affected when the low pressure parts of the waves try to accelerate it back towards it. Instead, this affected electron, one of the two outer ones, one is binding between atoms, and the other one is not binding. It's just stuck in a hole. When it gets hit by that hammer of the high pressure part of the wave, it accelerates outward, and whips around its nucleus, and it does orbit, because it was pushed. And that's the only reason any electron would ever orbit its nucleus, is if it was pushed. Now, it can orbit for a very, very long time, depending on how much debris is there, or if there's a lot, if there's a lot of debris, it will slow down. If there's not very much debris, it'll it'll keep orbiting. But anyway, what happens is, it absorbs the high pressure part of the wave coming in from the electron that was traveling through a wire nearby. It absorbed the high pressure part, but what it didn't do is it didn't absorb the low pressure part of the wave. So what happens is that low pressure part of the wave travels on, it hits a stuck electron in an atom, in the atom, perhaps closer to the nucleus, or perhaps the one binding between atoms. Whatever it crashes into, it absorbs that part of the wave, and what does it do? The low pressure part of the wave sucks the entire atom back a little. And so imagine if you had a whole lot of different waves coming in, and it keeps getting accelerated back towards the object, the source of the wave. And that's why iron sticks to a magnet. And so it's all about satisfying the wave. Which electron will satisfy the wave, in what circumstance it will satisfy the wave in, which proves that we really are all in an ocean of matter, and that all has to do with high pressures and low pressures. And it has, I mean, in physics, it's like weathermen would have been closer to the subatomic, the subelectronic truth, rather than physicists, because physicists are still thinking about, like, they have no idea that it's so simple, that it actually has to do with high and low pressures. It all has to do with the pile and the hole, and that's all that exists. Everything else, it's just bullplop. There's no such thing as physical, as physics rules, there's no such thing as forces. There's no such thing as properties to matter. There's no such thing as forces of matter. There's no such thing as fields. It's all completely explainable, and not what's believed today. And that could be a problem for people who don't believe in God, because it shows that the matter, physically speaking, could not be created nor destroyed. But it also shows, but of course God made it all, because he's the great spirit, and spirits don't have, are outside of matter, so that they can create. But the reason why atheists are not going to like this theory is because it's not a theory. It's completely explainable. Yeah. If you look into the pieces, this is not a guess. This is not guesswork. It's reality, based on what reality shows us, based on what nature actually tells us. It's not a theory, whereas other people have a theory and they have I have a guess. In other words, no, I didn't do any guessing. I looked at what was there, and understood it from what was there. Anyway, yeah. So this is different from theory. This is reality. What I want to say was, yeah, atheists would have a problem with this, because if you look at the very basics of things, you realize everything is based on the pile and the whole, and that doesn't leave room for one thing. It doesn't leave room for the spirit of a person, because the spirit of a person wants, wills, desires things, and you can't write that into the matter unless you inject a spirit into the matter, and God can do that, and that's what he did with our physical minds. So it's impossible to want anything if you're a rock, and these bodies of ours, they are just rocks. I mean, it's just made of round pieces of dust, just like everything is made of round pieces of dust of various step sizes. you know, the smallest step sizes, you know, the general pressure of the entire universe causes them to be that step size all the way up to the highest step size, and it's all predetermined by the general pressure of the entire matter universe pushing in and all. But what you can't get a rock to do, what you can't do, get a piece of matter that just simply exists, and that's all it does, is just exist. That's all it ever is, and all it will ever be is something that just exists. You can't get that little rock, that little marble, to do anything, to want, I mean, other than to just be. It always just is. And so if you think about that, if you realize that you can't make it want, will, or desire anything, and yet we do. In fact, that's the drive behind everything that we do. The fact that we're connected to the matter allows us to want physical things like food and water and other physical things that we want and need. But you know, disconnected from this body, I'm not going to want food anymore. But anyway, the fact that you can't put into the matter, people can't put into the matter a spirit, because you just can't get something to want, to will, to desire anything. You can't get a rock to want anything. And yeah. Now there's also these other theories that should be talked about, that people think are real but are not real. Like, for example, antimatter. There's no such thing as antimatter. You can't have a thing and then have the opposite of that thing. The opposite of having something is having nothing. The opposite of the pile is always a whole. And that's it. That's all there is in matter. There's no such thing as antimatter. And in the bubble chamber experiments, when they show like supposedly a positron colliding with a or like a, yeah, like an electron colliding with an anti-electron, or, you know, antimatter electron, or a proton colliding with an anti-proton, or what have you. What they're showing is a piece of stuff colliding with another piece of stuff, and it's a theoretical, mathematical prediction of what should happen. It's not reality, it's not real. And when they show the collision, what they're actually showing are two pieces of matter forced and colliding and breaking into little pieces. And I've seen the pictures for myself and the experiment for myself, and I see them labeling all the little pieces, and sometimes they'll even label some of the pieces that come off like energy or something like that. And I'm like, that's ridiculous. It's not energy. You just crashed two pieces together, and based on your theory, this was matter and this was antimatter. But that's not what's real. You can't have the opposite of a thing. It's just, you know, an opposite of having something is having nothing. Oh, and then there's the theory of dark matter. Dark matter is also not a thing. It's kind of a thing, but it's not. The matter's not dark. It's just, it's subatomic. It's so small that they think that it doesn't exist, and that's what antimatter is. It's I said antimatter. I meant dark matter. That's what dark matter is. Dark matter is something that's so. It's the stuff. In fact, most of the universe would then be considered dark matter, because most of the stuff in the universe is very, very small, and you're not going to be able to detect it by looking at it, because it's so small. You're using it to look with. You use it to see with, like photons. You know, that's light traveling as a wave. You know, high pressure part, low pressure part, you know. And so of the wave traveling through real stuff. And it would have to be real stuff, because there's nothing else for it to travel through. You can't have it travel through, you know, and they say, oh, it travels through a field, an electric field, a magnetic field. Well, then what is an electric field and magnetic field? Well, of course, I've already explained electric fields and magnetic fields, whereas magnetic fields are the circulating waves coming off of the electrons. What else? Okay, we did oh, dark matter is actually this small stuff. Yep. Let's see, magnetism, we did that. Diamagnetism, we did that. Boy, there's a lot more to talk about. Oh yeah, we talked about black holes, how they're actually full of stuff, and they're just, you know, they're large pieces of stuff which create, you know, great chains going way out into space. And yeah, it is kind of like a warping of space-time, but it's a warping of space-time matter. It doesn't warp it, it just creates arrangements, a large matter arrangements that go way out, and that's how it warps space-time. It's funny how Einstein was able to figure that out without knowing exactly what was actually going on. I'm impressed that he got that far without knowing what was actually happening. But yeah, good for him for explaining gravity using space and time. But if he was able to know that matter was space-time substance, you know, space-time matter, were all one thing and not three different things. He knew that space and time were one thing. Good for him for knowing that. But if he had known the third thing, he would have been able to figure out everything. You know, the whole thing, just like I have. Now I realize that there are multi-billion-dollar experiments going on out there. You know, with their super colliders, multi-billion-dollar projects that humans have made in order to understand what I've already understood, what I've already explained. And of course I have more to explain, but I won't explain it here. I think this video is also already way too long, but I'd like to include it. I don't want people to not know these things. And I do feel irresponsible for not if I didn't make this video, I would feel, I would feel like I wasn't doing the right thing. Because then, like, what if all of these mysteries of the universe, these secrets, died with me? That would be so irresponsible, and I couldn't. Well, I could say I couldn't live with myself if that happened, but I'd be dead. So if God called me home before I was able to explain this to people, boy, that would not be good on my part. So I made this video so that people could know, kind of, drifting on the surface of all these various different things, what's actually going on. That really is all just dust. And as the Bible says, dust. It's about Adam's body. For dust you are, and dust you will return. Now the spirit, of course, is not dust, and it lives on, and we'll be judged by God whether we did good or bad, whether we accepted Jesus as our Savior or if we did not, for the forgiveness of our sins. And hopefully everyone out there has accepted Jesus for the forgiveness of their sins, because that is infinitely more important than all physics understanding. Because here we live for a limited time, but there, if you're a Christian, if you have your sins forgiven, if you're living a good life, like he said to in the Bible, then you will live forever. And forever is infinitely longer than understanding or trying to make a heaven on earth. Here, it's all limited. It's all limited. Even, I know that the earth will go for thousands of years, but just as it's already gone for thousands of years, but infinity is infinitely more important than thousands and thousands of years. So, of course, inevitably, there's going to be a lot of things I didn't cover, but yeah, as it relates to time, linear time doesn't exist separate from the matter. In other words, you're not going to be able to time travel. Time travel is impossible. And the reason for that is because a piece of matter is a piece of space and a piece of time, but it's a piece of the forever present time. And that's why if you take a piece of matter and displace it in a line, you will get a linear time measurement out in seconds and minutes, that sort of thing. But you can displace that same piece of matter again and again and again, and as long as you displace it in the exact same way by having by moving it along, by moving it like this, and then you're displacing the matter in front of it. What you're doing is you're weighing the matter against this other matter that you're displacing, and so that's why you get a linear measurement out by displacing matter in a line, and that's why. Yeah, that's why linear time. The same thing happens in your mind when you record events. Like you think this happened, and then this happened, and then this happened, and then this happened in your mind, because in the neurons, that's exactly what's going on. You record the events as they happen, this, and this, and so it's recorded in a line in your mind. And so that's why we think in terms of linear time. But linear time does not exist separate from the matter. It has to do with linear matter displacement, whereas a chunk of time is a piece of the forever present, and so that's why you can take the same piece of matter and displace it. No matter how many times you displace it, if you displace it in the exact same way, you'll always get the same measurement out. It's like weighing the piece of matter, only instead of using a weight for it like you would with a substance, you're displacing it linearly with it's a time measurement of that piece of matter, and that's why without the matter you won't have a piece. You won't have time, and you won't have space without that substance. You don't even have space or time without the substance. Let's see. Okay, yeah. So yeah, it's impossible to time travel, and but it is possible to make any atom you want out of the ocean of matter, because like I talked about before, if you have like the ocean of matter is filled with all different kinds of particles. You got the small particles, the big particles. Of course, if you want to make something like gold, then I would start with particles that were already large, so that you don't have to make larger particles to jam together. That way you use less energy, which is really just matter shoving matter together. And so if you want to shove matter together, you don't need to use close materials. You can actually make any atom you want to, the nucleus of it, simply by using the ocean of matter and jamming the ocean of matter. Like, you know how people believe that that there's dark matter. Well, it's really just matter that's too small to see. If you jam that together, and it's everywhere, you know, in the universe. In fact, you can't have space unless you have matter, aka you can't have space if you don't have you know, this matter, this substance, this dust. And you can jam the fine dust together and make anything you want out of it. It's everywhere. And so, you know, it takes more energy to jam smaller pieces together, but you can do it. And you can literally make what appears to be gold, I mean what is gold, real gold, out of what appears to be nothing, or what other people would call dark matter. And aside from that, you can... I wouldn't use that technique if I was starting off to try to make something like gold or platinum, or you know, so something precious, or silver, you know, just to be useful, to be more conductive, like maybe for power lines or something. I wouldn't start with you know, the ocean of matter to compress. I would use an ocean of matter compression chamber, and I would first atomize atoms that were close to what the substance that you want to create, something close to gold, like I don't know, like mercury or lead or something. But and then what you'd end up with is some good gold. If you want to make gold, once you compress it, you can build it. Okay, so you'd want to atomize it first, like separate all the atoms from all the other atoms, and just powderize them, and then compress them. And the technique I would use would be magnetism reflected by probably a diamagnetic material, very, very powerfully, and as well as a lot of heat. So I would use heat and magnetism in and an ocean of matter compression chamber, and that way I could compress the atoms to be any size I want them to be. And you get, and with that technique, something like that. That's what I would try first, and then after you did that, you'd compress the, let's see, you compress them, and then you'd oh, right. You'd end up with radioactive, some good gold, but then you'd also end up with some radioactive gold, and that's inevitable because some of the gold will be between the step sizes, and some of it will want to degrade back into, say, like mercury or something. In order to get that right, though, then you'd have to fine-tune the compression chamber in order to, get out the good gold that's already not between stages. And the reason why these isotopes are radioactive is, again, because they're between step sizes. Because you remember how we talked about fusion and fission, where things tend to fuse if they're too small, and tend to fizz out if they're too large, and that's because of the ocean of matter, that they couldn't get densely enough around them in order to hold them together if they're fission, if they're radiating out. So what you have to do is then, once you get the gold, some gold, but some of it's radioactive, you take the radioactive parts, and then you compress or decompress them in the chamber. You have a chamber do compression and decompression, so that you get the right isotopes that are stable, and then your gold is no longer radioactive, and that's what you, or degrading to the lower value or whatever, and that's what you'd want if you wanted to make gold or silver or any other atom that you want. That's the technique that I would use initially. Also, yeah, because our minds are made of this physical substance, that our spirit's connected to our mind, and our mind is still made of this physical substance. Psychology, the basis of all psychology, is again the pile versus the whole, and the reason for that is because our mind has nothing else to build with other than the pile versus the whole. And so the basis of all psychology, if you want to help people with psychology, you can find out what's wrong with them always, every time, 100% of the time, if you can find out what the hole is in their life. If you can find out what the hole is in their life, then you can work on ways to fix that hole. Now, people sometimes fill that, whatever particular hole's in their life, psychologically speaking, which is in their mind, with certain things to fill it. And so if you know, it's like a puzzle. It's like a puzzle piece. In fact, everything's like a puzzle piece. Like you can look at the puzzle, and if you see that the piece is a particular shape, then you know what actually was supposed to go there and didn't go there, and that's why it didn't work out. So if you have the piece, you know what hole it's supposed to fill, and if you have the hole, you know what piece was supposed to go in that hole, and that's the basis of all psychology. And a lot of psychologists don't know that, because they don't realize that the mind is physical, and therefore all of the psychology, that the spirit is tied to, because the spirit is tied to this physical body, is based on the matter filling the hole. And so if you understand what caused the hole, then you know how to fix whatever's wrong with the person. And yeah, again, that's it for now. But yeah, those three things, I thought, wow, I should mention those too. Okay, but I think that'll do it for now. But if I think of something else, I'll come back. But there's always more. But I think those were kind of important things to mention, because yeah, in kind of a time capsule like this, that could help people in the future if I somehow fail to teach people adequately in the future with better videos. Maybe this video would help.